Good evening, students. Are you guys able to hear me? Are you all able to hear me?
Sure.
Okay. So we'll get started. So what was the last topic we were discussing yesterday?
Sir, we were discussing about a small bar magnet, sir.
Yes. I hope you guys are able to see me also, right? If I have to show some demonstration. Yeah.
Yes.
Okay. So we were discussing about a small bar magnet. Right. And what was the last expression that I wrote?
Sir, 2 nu naught capital M by 4 pi r cube.
Yes. So we would have discussed about the magnetic field due to a small bar magnet at the axial point. Is that right? So magnetic field due to a small bar magnet at the axial point, and what was the value? This was equal to 2 times mu naught divided by 4 pi r cube into capital M. Is that right? So we are not concerned about the derivation of how we have got this because it's not a part of your curriculum. So this value, if we remember, right, today we are going to start with an important topic, that is bar magnet as an equivalent solenoid. So bar magnet as an equivalent solenoid. In the sense, you are going to say that a solenoid and a small bar magnet, that is a small solenoid and a small bar magnet, are going to behave in a similar way, except the fact that a solenoid is going to be a temporary magnet and bar magnet is going to be a permanent magnet. That's the idea. Okay, I repeat it again. The topic is, please write it down, bar magnet as an equivalent solenoid. Right? I hope you have written it. Shall I proceed? Okay. As an equivalent solenoid. So when I take a solenoid like this, okay, when I take a solenoid in this way, okay, where the winding is very close to each other, then what I can do is I can say that there can be an imaginary line which is perpendicular to the cross-sectional area, which we'll call it as the axis of solenoid. Correct? Similarly, if you draw a line perpendicular to it through the center, okay, now what we are going to do is, on the axis of the solenoid, I'm going to consider a point P where we are interested to calculate the magnetic field due to this whole solenoid. Is that clear? So if I take the length of the solenoid to be 2L, okay, then I can say that the solenoid is broken into two parts. One is L and the other part is also L. One minute. Then the other part is also L. So from the center, I will say that this point P is at a distance R from it. Okay. So is this point clear? Any doubt in this? Okay. Now see, if I take a small portion, let's say of thickness dx at a distance x from the center of the dipole, center of the solenoid. Okay. If I take this thickness to be dx, now I'm going to define certain parameters I want you to concentrate on. Let the number of turns in the solenoid of length LB capital N. Let the number of turns in the solenoid of length LB capital N and the number of turns per unit length, that is small n, will be equal to capital N divided by L. Okay. So when I take it in this format, now listen to this. If I take this small portion of thickness dx and let's say the distance from here till this point is x. So I've already taken x. Sir. Let's say this distance is a. Okay. Now, how much is this a going to be? Is it not going to be r minus x? Accepted? Correct? No. Guys, are you there or sleeping?
Yes, sir.
Yes, sir.
No, no, what? You are not there, or you're sleeping now? So let the number of turns in the solenoid of length L be capital N and number of turns per unit length be capital N divided by L. Now what I will do is, magnetic field due to the small piece of thickness dx at point P is equal to how much? Now this is what we are going to define. So if I say the small value of magnetic field is dB, okay. Now what I'm trying to do is, due to the small portion that I've considered, right, due to the small portion dx, what is going to be the value of magnetic field at point P? Okay. So for that, how we will do is, we need to recollect the fact that if you have a circular current carrying coil and on the axis of it at a distance x from it, okay, if there is a point P, then the magnetic field due to the circular current carrying coil is given as mu naught Ni a square divided by 2 into a square plus x square the whole power 3 by 2. Okay, mu naught Nia square divided by 2 into a square plus x square the whole power 3 by 2, where a is going to be the radius of the circular path and I is going to be the current that is flowing through the wire. Then what is going to happen to dB? dB will be equal to mu naught into the number of turns in this case will be capital N into the current I multiplied with let me take the radius of the solenoid to be small a. So n into I into a square divided by 2 into a square plus. Tell me what is the value of x in this case? Sorry? It is r minus x the whole square. Correct? Huh? So x is what? X is the distance from the center of the current carrying conductor to the point where you're trying to calculate the field. Okay. So mu naught n I a square divided by 2 into a square plus r minus x the whole square, the whole power 3 by 2 is the value of dB. Right. Now what I will do is I'll calculate the value of B itself. So what is going to be the value of B? For that, I need to check if everything is in terms of, if every value on the right hand side is in terms of one variable. Okay. First, let me call this as equation number 1. Okay. Now, points to be noted are, first, R is very much greater than X and R is very much greater than A also, because this is a small solenoid. Try to understand, in the previous lesson, we learned about the magnetic field due to a solenoid, but there it was a long solenoid, whereas in this case, it is a small solenoid. Okay. R is very much greater than A. Okay. When that is the scenario, now listen. I can say in first equation, dB will be equal to mu naught into, okay, I'll write one more step. When small n is equal to capital N divided by L, then the number of turns in thickness dx is how much? The number of turns in thickness dx will be equal to small n into dx. Okay. So here, if I take a small correction, guys, it's not n, it is n dash, because it is the number of turns in that smaller value. So n dash. So I'll call this as n dash. So if I use 2 in 1, what am I going to get? I'll get dB is equal to mu naught into small n into dx into I into a square divided by 2 into a square plus r minus x can be approximated to r itself. So r square the whole power 3 by 2, since r minus x is approximated to r itself. Now what we will do in the next step is dB will be equal to mu naught into small n into dx into ia square divided by 2 into r square the whole power 3 by 2, since a square plus r square can be approximated to r square, right? So when you write it like this, then dB will be equal to mu naught into small n into dx into I a square divided by 2 times r cube. This is the value of dB. Okay. So I suggest everybody to make a note till this point and ask me if there is any doubt.
Can you scroll up a bit, sir?
Sure. Is this fine?
Yes, sir.
Okay. Is this clear? Okay. Now our job is to find the value of B. So for B, what we will do is we will integrate on both the sides. Integrate on both sides with respect to x1. So when you do that, B will be equal to integral of mu naught small n into I into a square divided by 2 times r cube into dx. But where is the value of dx varying from? So dx is varying from, if I take this to be the origin, it varies from minus L to plus L. Okay. So when it is varying from minus L to plus L, the limits will be minus L to plus L like this, and B will be equal to mu naught n I a square divided by 2 r cube out of the integral. So from the integral minus L to L dx, this will be equal to mu naught n I a square divided by 2 r cube into integral of dx is going to be x from minus L to L will be 2L. Okay. Now listen. What is this small n into 2L? This is an important point. I want you all to concentrate. So B will be equal to mu naught into small n into 2L into I a square divided by 2r cube. Correct? So this will be equal to mu naught into capital N into I a square divided by 2 times r cube, since small n into 2L is equal to capital N. Okay. Now multiply and divide with pi, or I'll say you can multiply and divide with 2 pi itself. Then B will be equal to mu naught n into I into 2 pi a square divided by 2 into 2 pi into r cube. Now this expression will be equal to mu naught. So I'll take this 2 outside. So 2 mu naught into n into I into pi a square divided by 2 into 2, 4 pi r cube. Now tell me one thing. What is n into I into, what is pi a square? What is pi a square? Pi a square is going to be the area of cross section. So when it is considered to be the area of cross section, then B can be written as 2 times mu naught into n into I into A, the whole divided by 4 pi r cube. What is this n into I into A, guys? So this will be 2 into mu naught into, what is the value of number of turns multiplied to the current and area? It is going to be capital M divided by 4 pi r cube. So what is this expression? This is the value of magnetic field produced along axial point due to a small solenoid. But what is this output looking like? So what is this output looking like? So is it not similar to the small bar magnet? B axial for a yes or no? Is it clear? So first copy it. How is NIA is equal to M? That is the definition of magnetic dipole moment, no? Number of turns multiplied with the current and area. Yesterday's derivation also we used it for electron. Subhajit, you got it here. Current multiplied with area is magnetic dipole moment. If you add the number of turns for it, that is also dipole moment only, magnetic dipole moment. That is why I wrote it as capital M. J, that is for permanent magnet. Here we are dealing with solenoid. I told you yesterday, there are two formulae. M into 2L is for permanent magnet. N into I into A is, got it? Good. Good. Right? So I hope everybody has copied it. Right? So we'll move on to the next concept. So as I told you in the beginning, this chapter is basically divided into three parts. Okay. The first part is about bar magnet. Okay, that is the first part. And the second part is about Earth's magnetism, which is also called as terrestrial magnetism. So this is the second part. And the third part is called as magnetic properties of a material. Okay, it is magnetic properties of a material. Okay, so we will start discussing this first. So we are done with the first part. Now we are going to discuss about the magnetic properties of a material. Then we will go to Earth's magnetism. Okay, so I'm just giving you a disclaimer before itself. The terms that are used in this magnetic properties of a material are very much similar. Okay, they sound very much similar. So I want you all to pay utmost attention to ensure there is no confusion. Okay, so concentrate. Just give me a minute. Okay, listen to this. So the topic is magnetic properties of a material. So under this particular section, right, we will be discussing about the different kinds of magnetic materials that we have. So if you see in your chemistry, right, there is a chapter named solid state, which is deleted again this year. So under solid state, right, depending on certain structural arrangements, you can talk about the magnetic properties of a material also, which are basically classified as paramagnetic, diamagnetic, and ferromagnetic substances. Have you heard these terms anywhere? Have you heard of these terms, paramagnetic, diamagnetic, and ferromagnetic anywhere?
The paramagnetic is attracted by the magnetic field.
Correct.
Then diamagnetic is repelled by it.
Correct. Then what about ferromagnetic?
Don't know.
Ferromagnetic and paramagnetic, they both are similar, except the fact that paramagnetic is weak magnetism, ferromagnetic is of high magnetism. Ferro refers to iron, right? Ions are better magnetic materials. So here, to avoid the confusion, right, the first point that I want you to note is when you talk about a bar magnet, it is a permanent magnet, right? It is going to have the magnetic property associated with it for a longer duration. Now, when I talk about magnetic properties of a material, we are going to talk about different kinds of materials like aluminum, copper, iron. All these materials are classified into three categories, which I told you, basically para, dia, and ferromagnetic, right? Before we start understanding what a paramagnetic, ferromagnetic, and a diamagnetic substances are, we first need to answer certain questions related to how can those materials be magnetized in the first place. Okay. So here, if you see, there are 8 terms that we are going to learn. Out of those 8 terms, if you see, few terms will be concerned with respect to the field that is creating magnetism in a material, and few terms are concerned with respect to how much magnetism is created in a particular material. Okay. So if you see, the topics that we are going to discuss are, we are going to discuss about magnetizing field, magnetic induction, intensity of magnetization, magnetizing field intensity. We'll be discussing about magnetic permeability, relative permeability, and magnetic susceptibility. Okay, the last part would be about the relation between relative permeability and magnetic susceptibility and magnetization. We'll be seeing about all those terms. By now, you would have understood that the terms are sounding very much similar and close to each other, right? So we need to be very careful about understanding these things. So as I told you, concentrate, guys. First is, we are going to discuss about what is magnetizing field. So in yesterday's class, I would have told you one important point that if, let's say, this is a steel bar, okay? Let's say there's a steel bar and you have a magnet, okay? This green color bottle is a magnet, for example. If I take the steel bar and rub it against the magnet, right, for some amount of time, okay, then I take this magnet away. Now I have the steel rod in my hand. Initially, if you see, before we rub, right, if you take the steel rod closer to iron particles, it will not attract. But after you follow this kind of a practice, you rub it for some time and you, my camera is not off, my camera is not off. Are you guys able to see? Mine is pinned. There'll be 2 learning rooms. One will be with the logo and the other one, you try to search for it, no? Got it? Okay. So I repeated. So take a steel rod, rub it against the surface, and you try to take it closer to some iron particles, right? You can see that the steel rod would have acquired the property of attracting, right? So where has the steel rod got the magnetism from? The answer to that is very simple. Where is it got from? From this permanent magnet, correct? Is that right? So when you take a magnetic material, so here the magnetic material is not magnet. The magnetic material is the steel rod which I was talking about. So when you take a magnetic material and you place it in the presence of external magnetic field, okay? So what would have happened is, if this is a magnet, for example, right? Let's say this is North Pole, this is South Pole. Then the magnetic field would have been from north to south outside the magnet, and inside it would have been from south to north. So if I take this rod and keep it in the presence of magnetic field of this bigger magnet, then what will happen is the steel rod will start acquiring some magnetic properties. So that is what we are trying to say. When a magnetic material, in this case the steel rod, is placed in the magnetic field, then there is some magnetism induced in the steel rod. Okay, so I hope it is clear till this point. We are able to understand that the presence of magnetic field through a material, if magnetic field is passed through a material, you can induce magnetism in it. Okay, then the field that is there now, which is able to induce magnetism in the material, that is what is called as magnetizing field. Name itself is suggesting magnetizing field means it has a tendency to magnetize a given material. Is that clear? So if you're clear with this point, then I'll tell you. So there are two ways in which all the terms will generally be defined. One is in terms of general English, and the second is in terms of some mathematical parameters. So if you observe, the magnetic field that exists in vacuum and induces magnetism means if there is a magnetic field which can create magnetism in another material, then that is called as magnetizing field. Okay, for example, if I consider a toroidal solenoid which is carrying a current I and is placed in vacuum. So let's say there is a solenoid, for example. Let us forget about toroid also. Let's say there is a solenoid and around this there is a wire. Okay, and let's say there is an iron core. Now, when you pass the current through the wire of the solenoid, what will happen? There will be a magnetic field existing within the solenoid, right? And what is the value of the magnetic field that is within the solenoid? I can say B naught is equal to mu naught into N into I. Now, when this magnetic field of mu naught into N into I is passed through the steel rod, what happens is magnetism is induced in it. So in this case, this B naught is equal to mu naught into N naught, N into I is what is called as the magnetizing field. Is it clear? Is it clear, guys?
Yes, sir.
Okay.
Yes, sir.
Now, when you do this kind of a process, what happens? An output is generated, right? Means this material is now magnetized, right? Now, imagine there is magnetic field created within the steel rod. Apart from that, you also have the magnetizing field. I repeat it again. You have magnetism induced in the steel rod and you also have magnetic field present, the magnetizing field present, right? So if you are able to calculate the vector sum, okay, if you are able to calculate the vector sum of the magnetizing field plus the induced field, then this is what is called as magnetic induction. Okay. So are you able to understand the basic outline of it? So what is basically magnetic induction? Magnetic induction is the vector sum of the magnetic field that is creating the magnetism and the value of magnetic field created inside a material. When you add these two values in the vector form, then that is what is called as magnetic induction. Okay. Now, what happens inside a magnetic material that we will see? For example, if I have a toroid which is there, okay, and these wires are wound around a magnetic material. That magnetic material can be anything. It can be aluminum, it can be copper, it can be iron, whatever it is. Okay. Now, when the toroidal solenoid is wound around a ring of magnetic material, then under the influence of the field B naught, what does this B naught stand for? What is this B naught called as? It is called as magnetizing field. Generally, when you put a knot, that is called as magnetizing field. Due to this magnetizing field, what will happen is there will be magnetic moments of the atomic current loops of the magnetic material. So this material is there, no, the magnetic material that will by default be able to exhibit magnetism. Why? Because it also has atoms. Yesterday I told you, wherever atoms are present, magnetism is going to exist. Okay. Now what will happen is magnetic moments of the atomic current loops of the magnetic material will start aligning themselves with or against the magnetizing field. In the sense, if the magnetizing field is in this direction, then the alignment of magnetic field inside the magnetic material can either be in the direction of magnetic field, in the direction of B naught, or in the direction opposite to B naught. So generally, the induced magnetic field inside the magnetic material will be in the direction of B naught for paramagnetic and ferromagnetic substances, but it will be in the direction opposite to it in the diamagnetic substance. Okay. Now what will happen is this magnetic field will give rise to a net current on the surface of the metal. So you have the surface of the metal, right? So on the surface of the metal, what you can observe is you can observe some value of current that is getting generated, which we call it as magnetization surface current, which is given by the formula I with a subscript M. Okay. Then this current induces magnetic field Bm, which is given by the value mu naught into small n into Im. And this value is called as C. Yeah. So this is the value which is the induced value. Due to whom? This is the induced value due to whom? Due to the surface magnetization current. Okay. So this value is important. Please make a note of this term. Now what you can do is the total magnetic field inside a magnetic material, the total magnetic field inside a magnetic material is what? It is the sum of the external magnetizing field and the additional magnetic field produced due to the magnetization. So the induced magnetic field, you can write it as mu naught into n into I plus mu naught into n into Im. Okay. And this sum is what is called as magnetic induction. Okay. So if you see the SI unit of magnetic induction, it is going to be Tesla or Weber per meter square, which is also equivalent to Newton per meter per ampere or Joule per ampere per meter square. These are all the SI units which are related to the magnetic induction. So make a note of this. Okay. The next term that we are going to see is magnetizing field intensity. If you see the word magnetizing, that is always so. Is it enough? Nitin, is this enough? Okay. So next is magnetizing field intensity. So wherever you see the word magnetizing, it is something related to the input value. Okay. The ability of magnetizing field, that is the input field, to magnetize a material medium is expressed by a vector quantity H. And that H is what is called as magnetizing field intensity, or in simple terms, you call it as magnetic intensity. Okay. So we already saw that the value of magnetizing field intensity is mu naught into N into I. By the way, I want to stress on one point. This is not a standard formula for magnetizing field intensity. There is only the magnetizing, sorry, this is not the standard formula for magnetizing field. So the standard formula for magnetizing field depends on okay, the value for magnetizing field depends on what kind of a material you're using. So here in this case, it is for a solenoid. Okay. If you use some other material, then it will change accordingly. So this is equal to, yeah. Now, if you see in this, you have small n into I, right? The small n into I is what is called as H, or you call it as magnetizing field intensity. Okay. So the permeability multiplied with the number of turns and the current is what is called as H. And that H is written as N into I. Okay. Then if you observe this expression, B naught is equal to mu naught into N into I, or you can write it as mu naught into H. Then capital H can also be written as B naught divided by mu naught. Okay. So what is going to be the SI unit of it? SI unit of it will be ampere per meter, which is also equivalent to Newton per meter square per Tesla, or joule per meter per WB stands for Weber. Okay. So is that clear? So is that clear? Now listen. So the next term that we are going to see is called as intensity of magnetization, or in simple terms, just magnetization. We call it as intensity of magnetization, or in simple terms, we call it as magnetization, right? So when a magnetic material, you place it in a magnetizing field, it gets magnetized. But now the question is, what is the extent to which the material has got magnetized, right? Suppose I take this to be the steel rod. So when you place something in the presence of external magnetic field, let's say B naught, then this B naught will create an induced magnetic field inside. Okay. And due to the induced magnetic field, what will happen is there will be a dipole moment existing inside it. Right? So I'll call it as small m vector. Right? Then the value of the magnetic dipole moment per unit volume of that material is called as capital M vector, which is also called as intensity of magnetization, or in simple terms, you call it as magnetization. Okay. Now, from this, an important point that we can conclude is that magnetic induction is equal to the sum of magnetizing field and induced field. Okay. Then what you can write is, then you can write B will be equal to mu naught into capital H, which is the value for magnetizing field, plus mu naught into capital M, which is the induced field. So magnetic induction can be written as mu naught into capital H plus capital M. Okay. So the next term that we are going to see is magnetic permeability. So magnetic permeability, as the name suggests, it is going to speak about the measure of the extent to which a material can be magnetized. Okay, or the extent to which the material allows. So here M is no. Which M? This M, right? So you're asking about capital M, right? So here capital M refers to intensity of magnetization. So I've written it here, no? Intensity of magnetization. This value is intensity of magnetization. And this M represents dipole moment. Okay. So the amount of dipole moment created per unit volume is what is called as intensity of magnetization, or in simple terms, we call it only as magnetization. Subrajit, I hope I answered your question.
Sir, can you tell sir, dipole moment per unit volume?
Dipole moment per unit volume, see. The magnetic moment developed per unit volume of a material is called as intensity of magnetization, or simply magnetization.
Okay, sir.
Means if this material is there, okay, I take a unit volume of it, I break it into, let's say I can break it into 10 unit volumes. Okay, if I take one unit volume, if I take a unit volume, and if I'm able to calculate the amount of dipole moment created in that material and divide it with that volume, then that is what is called as magnetization. Nitish, are you able to understand?
Sir, magnetic dipole strength is represented by what letter, sir? Like
Ampere
capital
meter
or?
square. Which one? See, that varies from place to place. Okay. So, in this context, we are representing dipole moment with small m. So, I understand where the confusion is coming from. Listen to this. When you talk about the bar magnet concept, right? In the bar magnet, we would have used small m for pole strength and capital M for dipole moment. Whereas, when you talk about the magnetic properties of a material, Okay, when you are speaking in terms of magnetic properties of a material, then small m is used for dipole moment and capital M is used for magnetization. I hope this answers your question,
Yes, sir.
right? So that small m and capital M will vary from context to context. So from topic to topic, it keeps changing. So in this context, capital M stands for intensity of magnetization and small m stands for dipole moment. That's it. Is that clear?
Clear. Yes, sir.
Okay. No. So I gave you a formula. B is equal to mu naught into capital H plus capital M, right? Let's see how we actually got it. So when I say intensity of magnetization, it is defined as the dipole moment divided by volume. So what is the formula for dipole moment? Capital N into the magnetization current into area, N into I into A, divided by the volume is going to be A into L. Accepted? So generally, if you take all the magnets, right? Generally, the length is written as 2L because you treat them like small dipoles. I already told you why we use 2A or 2L. Because when you do the derivation, the center can be taken as origin and either side can be of the value L and L. Okay. So capital N divided by 2L will give you what? Small n. A and A will get cancelled. So small n into Im can be called as intensity of magnetization. So intensity of magnetization is small n into Im. But I already told you a formula here. Bm is what? Bm will be equal to mu naught into n into Im. So what can I replace this n into Im with? I can replace it with capital M. So Bm will be mu naught into M and B naught will be mu naught into H, as a result of which, when you talk about the magnetic induction, it will be mu naught H plus mu naught M. Is that clear? Okay, there is also an important expression. Please remember it. Next is magnetic permeability. So when I say magnetic permeability, it is the extent to which a material will allow magnetic field to penetrate through it. Okay. Then you can define magnetic permeability as the ratio of magnetic induction to the magnetizing field intensity. So magnetic induction is output, magnetizing field is the input. So B divided by capital H is what is going to be mu. Okay. Now what will be the SI unit for it? Tesla per ampere per meter, or it is going to be Tesla meter per ampere. Okay. So like how you have magnetic permeability, you also have something called as relative permeability. So relative permeability, as the name suggests, it is written as mu r. So relative means division of magnetic permeability of a material to the magnetic permeability of free space. So it is defined as the ratio of permeability of a medium to the permeability of free space. So this is mu r is equal to mu divided by mu naught. Okay. So then you have a term called as magnetic susceptibility and the relation between magnetic permeability and magnetic susceptibility. That I will explain in the next class. Okay. So yesterday, who asked me about that surface tension problem when an air bubble is given? Is it Harini?
Yes, sir.
Okay. So listen now. So when you take an air bubble, right? Sorry, soap bubble. When you give negative charge to it, so for that matter, you give any charge, right? According to the properties of conductor, this is hollow in nature. So when it is hollow in nature, where is the charge going to go and sit? It will sit only on the surface. Is that right?
Yes, sir.
Okay. So do you know this concept of excess pressure? Don't worry, generally in boards you will not get this tough question, but since you asked, I'm telling the answer for this. So you know about the excess pressure, which is written as 4T divided by R.
Yes, sir.
So where T stands for the surface tension. Okay. So generally, if you look at the phenomenon of surface tension, right? Surface tension always tries to reduce the surface area. Do you know this concept?
Yes, sir.
So surface tension will always try to reduce the surface area. But since now, in this scenario, all the charges are going and sitting on the surface, this negative charge and negative charge will repel, and this negative charge and the negative charge will repel, as a result of which the force, the electrostatic force will act in the outward direction, and surface tension will act in the, and the force due to the surface tension will act in the inward direction. Okay, which I can call it as P into 2 pi r. Okay, if I take one layer of the surface, generally a sphere is a three-dimensional surface. So if I consider it to be a circle in one of the parts in projection, I can write it as T into 2 pi r. So the electrostatic force, since it is acting in the outward direction, what will happen is radius will increase only. So that was right. Okay. So irrespective of whether you give negative charge or positive charge to a soap bubble, please make a note of this point that the radius will always increase, and it is happening due to the electrostatic repulsion taking place between the surface charges. Is that clear?
Yes, sir.
Yes. So there is a logic. So if there are generally these kind of questions come in advance, because you have to integrate and then solve all these problems. But anyways, if you see it as a theory, if at all any of you get this question in your exam, right? Irrespective of whether you give negative charge or positive charge to whom? To a soap bubble. Okay, because there are two kinds of things. One is you can give it to a soap bubble, or you can give it to a water drop also. When you talk about a water drop is a complete sphere. Whereas when you talk about a spherical bubble, soap bubble, it is a hollow spherical shell. So for those shells, the charge will go and sit on the surface, and the radius will tend to increase. That's it. Okay. So that's it, guys. See, about the pollination one, I'm not sure. Okay. So any other doubt? So today, I suggest you all to go through these topics again, because tomorrow I'll show you a small video where an experiment is done, based on which we will classify the materials as paramagnetic, diamagnetic, or ferromagnetic. But for you to understand that, you need these terms. If you understand these terms, the classification can be done in 20 to 25 minutes. Okay, so tomorrow mostly we'll be doing about the classification, and the second part we are going to deal with is Earth's magnetism. So tomorrow we'll complete this chapter. Okay, so revise and come. So that's it, and we'll wind up.